Hi everybody, Mrs. White here. Today we're going to take a look at the tools that we've been exploring that can help us find missing sides of right triangles. And we really want to be careful here. These tools are only good when we know that there's a right angle in the triangle. So let's start with the first tool. That's one that you've been using for a little while now, the Pythagorean theorem. Specifically, Pythagorean theorem is a tool that we can use when you already know two sides of the right triangle and you're trying to find the third one. And in both of these problems right here, we can see that we know two sides and the third one is unknown. And this is the time we want to use Pythagorean theorem. So over here we have Pythagorean theorem, a squared plus b squared equals c squared. This picture is kind of nice. It really shows what Pythagorean theorem means more visually. If we envision squares being drawn off the three sides of a right triangle, then what Pythagorean theorem really says is that the area of the two smaller squares adds up to the area of the larger square. In other words, we could cut up these two smaller squares and they would perfectly fit inside that larger square. So when I look at this first problem right here, I want to first make myself find the longest side, the hypotenuse. There's my 17, so that's my C. And that means the other two sides would be my A and my B, the legs of the triangle. So now I can set up my equation, a squared plus b squared equals c squared, or in other words, x squared plus 15 squared equals 17 squared. And now I can go and simplify both sides by squaring the numbers. 15 squared is 225, 17 squared is 289, and now I can use some of my inverse moves, my undoing moves, to isolate the x. So subtracting 225 from both sides, and then undoing the square by taking the square root. And in doing that, I now know that the length of this missing side must be 8 in order for that angle to truly be a right angle. Here's another one. Just slightly different numbers, and also notice this time it's the hypotenuse that we don't know. So that longest side, the x, is going to be on the side by itself. That's our c. So when I set up Pythagorean theorem, we've got 2 squared plus 4 squared equals x squared. I can go through the same moves, square both numbers, add them together, and now I have 20 equals x squared. I can again undo the square by square rooting both sides, and now I know that x is the square root of 20. Which as a decimal is about 4.47. That's an irrational number. We can do a little better than that and keep it exact instead of having to rely on this rounded decimal. In order to do that, I can take that number 20 and try to break it down into the product of two numbers that equals 20. And I specifically chose 4 and 5 because 4 is actually square rootable. The 5 is not, but the 4 is. And so when I take the square root of 4, I get 2. The square root of 5, I can't square root it without getting a decimal, so I'll just leave it square root of 5. And so a better answer to this problem, an exact answer, would be 2 times the square root of 5, which also has that same decimal value of 4.47. We also looked at 3 other tools last lesson that deal with what to do when we only know one side, but we also happen to know an angle. And this is when trig ratios come into play. So if we know the length of one side, we also have an angle, then we can use these fixed trigonometric ratios to find the missing side. So in this first one right here, if I wanted to solve this problem, I'm going to first focus on this 32-degree angle and really make sure I'm aware of exactly where it is in the triangle. And now my job becomes trying to decide if this 18 is the opposite, adjacent, or hypotenuse. In this case, that's the hypotenuse because it's across from the right angle. And now this one here could either be opposite or adjacent, but because this is a 32, the 32 is right here, now it's next to it, making it adjacent. If I moved the x over here, it would be opposite. If I moved the 32 over here, it would be opposite. But in this situation, the x is adjacent. The 18 is the hypotenuse. And so using that SOHCAHTOA acronym, when I see adjacent and hypotenuse, that's my cue to use cosine. And so in this problem, I'm going to take cosine of my angle, always cosine of an angle, that's my input, and then set it equal to that constant ratio of sides. In this case, adjacent over hypotenuse, x over 18. And now I just have to think about my algebra moves that help me isolate that x. And in this case right here, x is being divided by 18, and so I can multiply both sides by 18 to isolate the x. At this point, I'll pick up my calculator, type that in, and I get 15.26. If you try typing this to your calculator and you do not get 15.26, double check to make sure your calculator is in degree mode. That could be part of the issue. Okay, let's look at two more here. This problem right here, again, I'm going to focus on my angle. And when I look closely at these sides, I see that the 10 is opposite. The x is next to the 51, so adjacent. And when I think about my trig ratios, that's my TOA. Tangent is the ratio of the opposite side compared to the adjacent side. So now I know this is a tangent problem. And so when I set this up, I'll take tangent of my angle, tan 51 equals, and then we'll set up the ratio in that order, opposite over adjacent, just like the ratio in the rule says. Only difference this time is the x is in the denominator, and so we have a little extra work in this problem. I'll need to multiply by x to undo the division, and now the x is still not isolated, so we'll divide both sides now by tangent of 51 to undo this multiplication that we see right here. And now I can pick up my calculator. 10 divided by the tangent of 51 gives me 8.10, which would be the correct length of this missing side right here. In this third problem, we're now trying to find x, and I'm noticing it's the hypotenuse. So right away, I'm thinking it's got to be sine or cosine. Tangent does not even involve the hypotenuse. And more specifically, when I look here, the 200 is across from or opposite the 42. So this makes this a so or a sine problem. And so this time I will set up the problem as sine of 42 equals the ratio opposite over hypotenuse in that order, 200 over x. And like in the last problem, we have the x in the denominator, so we need a double solving move where we first multiply by x to undo the division, and then we continue dividing to undo the multiplication. One last problem just so that we can see why trig ratios might be useful in context. So here's a problem. Jenny stands near a 50-foot tall tree. A bird sitting at the top of the tree looks down at Jenny's head at an angle of depression of 38 degrees. If the top of her head is 5.5 feet above the ground, how far does the bird have to fly to land on Jenny's head? So quick little side conversation. Let's talk about what it means to describe the angle of depression. And let's look at this little picture up here. Let's suppose we have a little bug sitting on the ground and a little bird up here, and that they're both looking at each other. So here's that line of sight. The angle of elevation is the angle at which the bug would have to rotate its head to see the bird. The angle of depression is the angle at which the bird would have to rotate its head to see the bug. And conveniently, the angle of depression and the angle of elevation are the same. They would both need to rotate their heads the same amount to see each other. We can prove that those angles are the same using some geometry properties that involve parallel lines and alternate interior angles that must be congruent. So the angle of depression equals the angle of elevation. So now when I look at this problem here, it always helps to draw a picture when we have a word problem like this. So here we have Jenny standing on the ground, and I'm labeling that her head is 5.5 feet above the ground. I've got this tree over here that's 40 feet tall with a bird up top. And now here's where we need to be careful. The bird is rotating its head 38 degrees downward to see the top of Jenny's head. That 38 degrees, notice, is kind of outside the picture if we're starting to visualize a triangle right here. But conveniently, that 38 I could also place down here. That would be the same angle that Jenny would have to turn her head to see the bird. Another option would be to subtract from 90. This is a right angle right here, and I could get myself into the triangle that way. But I'm going to just stick with this 38 down here. And now I'm trying to find the distance the bird would have to fly to land on Jenny's head, so I'll label that with a variable. That's my unknown. When I come over here, I knew that the total height of the tree was 40 feet, but I also know that Jenny's head is 5.5 feet off the ground. So if I subtract those two numbers, the remaining height of the tree, which is the part inside this triangle, is 34.5 feet. And now I can really focus on this triangle right here, and I'll redraw it down below. If I look at this triangle, I have a triangle with a 38-degree angle. This is a right angle, assuming the tree is standing straight up. I'm trying to find the hypotenuse, that flight distance, and I know that the part of the tree that's actually in this triangle is 34.5. Now it becomes a problem just like all the others. I want to focus on my angle, decide if my relevant sides are the opposite, adjacent, or hypotenuse. And in this problem, we're dealing with the hypotenuse and the side opposite the angle. And so this is a so or sine problem. And so when I set up my problem, I'll take sine of the angle, set up the ratio opposite over hypotenuse, and once again we see a problem with a double solving move where I need to multiply by d to undo the division, and then use division to fully isolate the d. And now I know that this bird has to fly just over 56 feet to land on top of Jenny's head. This has been a summary of the tools that we have that allow us to find missing sides of right triangles.